Hi all, this is Basic Searches and Graphs. So graph searches, we call them searches, but really they're like traversals. We're going to have an algorithm where we visit every vertex. And if we find what we're looking for before we visit all of them, we can stop the traversal and we can say we found it. But the logic of the thing is really more of a traversal, and that's what I'll show you. Keep in the back of your mind that if you're searching for a particular thing, instead of visiting everything, that you may return out of the middle of this. So we have two types of searches. We have a depth-first search, and that stores its progress through the graph on a stack. It tries to get away from its starting point very quickly, and it hopes to get lucky. And it uses backtracking to make sure it covers everything. Think back to the teddy bear problem. We're trying to design the thing so that it would check all the possible paths, and that's what a depth-first search will do as well. Now, if there's more than one path to the answer, more than one answer that's correct, depth-first search doesn't guarantee we'll find the shortest one or the quickest one. It'll simply go until it finds one of them and then quit. And for some problems, that's all we need. Our other possibility is the breadth-first search. You'll see it's very similar, except it stores its progress through the graph on a queue instead of a stack. And that means it visits things in a different order. And in particular, it means it'll find the shortest path from the starting goal first. If there's more than one good goal or more than one path to a goal, it'll quit when it finds the first one, which the depth-first search will do as well, but it'll find the shortest of the paths first. Now, either breadth-first search or depth-first search can be used with either of the representations we talked about, either the adjacency matrix or the adjacency list. And from here on, we're not going to really worry much about the representation. We're going to assume that that's been done and been done correctly, and that we have some kind of a nice simple interface into it, so we can abstract our graph and just worry about it in terms of nodes and edges, and not worry about it in terms of a number in a two-dimensional array or a linked list or any of that. We're going to assume that we hide all that. So this is a kind of modularization using layering, and that'll end up becoming important to us later. So onwards. So this is an example graph. This is right out of LaFour, and so if you have trouble following me, I try to be clear, but if you have trouble following it, you can also work through the same problem with the depth-first search and the breadth-first search from LaFour as well. That's where I got this particular one. Now we consider this to be a graph, even though technically it's kind of a tree, right? If I assume that A is the root, then everything, nothing has more than one parent, although A, of course, has a bunch of children. But we've seen some trees that do have a bunch of children. In general, if it's more than a binary tree, and the exception, the obvious exception, of course, is the capital B trees, if it has more than one children, we'll just treat it like it was a graph rather than really try to develop specific logic for it to be some kind of a multi-way tree. And of course, that's very much a generalization. So let's start with the depth-first search. We have these three rules. Rule 1, if possible, visit an adjacent unvisited vertex, mark it and push it on the stack, and then move to the visited node. Rule 2, if you can't follow Rule 1, then if possible, pop a vertex off of the stack, right? So as we visit nodes, we mark them that we visited them. We'll do whatever we were supposed to do in visiting them. We'll mark them that they've been visited. We'll push them onto the stack. Okay. Rule 2, when we're out of things to visit, then if we've got stuff on the stack, we'll pop something off of it, make that our current node, and see if we can work from there. Rule 3 is if we don't have any unvisited vertexes that we can get to, and we don't have anything on the stack, then we're done. Now, in theory, we could start with any node in the tree and we would ultimately visit all of them. But just to make it a little easy, and in part because LaFour does this order, we're going to start with vertex A. And so we start with vertex A. We could have picked a different vertex. You can work through these rules for a different vertex. And we're going to start visiting. We're going to follow rule 1. So we're going to start with A, and we're going to visit it, mark it, and put it on the stack. You'll see down at the bottom there I've got my stack that I'm building. And then I'm going to pick a node that I haven't visited that I can get to from A, and I happen to pick B. Once again, I could have picked something else. We would eventually, following these rules, visit everything. But I'll start with B, and I'll go to B and visit it, mark it, and push it on the stack. And then I'll see if there's anything I can visit from B. Well, there is. I can go to F. F hasn't been visited yet. So I'll visit it, mark it, put it on the stack, and then I'll ask the question, is there any place I can visit from here that I have not visited yet? And the answer is yes, I can go to H. So I visit H, I mark it, I put it on the stack, and I look around for something else to visit, and there's nothing left that I haven't visited. So I can no longer apply Rule 1. You'll see where I've gotten the stack to at this point. I've got H, F, B, and A on my stack. I can no longer apply Rule 1, so I'm going to go back and do Rule 2. So here's where we were. I got Rule 2, and if you can't follow Rule 1, and that's where we got to, if possible, pop a vertex off the stack. So if the stack's not empty, I'm going to pop a vertex off, and I'm going to go to that vertex, and I'm going to try to apply Rule 1. So I'm going to pop H off, and I'm going to try to apply Rule 1, but it has no unvisited adjacent vertex. So I pop the stack again. So I pop F, and I look at F, but it has no unvisited adjacent vertex. You'll notice I'm backtracking here. So now I'm going to pop B. It has no unvisited adjacent vertex. So I'm going to pop again. This time I pop A, and it does have something that we haven't visited. It's got a number of things that we haven't visited, and that means we're ready to go back and to apply Rule 1. Notice that we had worked our way down to H, and then we backtracked our way up. And if there had been some other branch, like maybe if F had had a second child, we would have come down that branch before we finished backtracking all the way up to A. In this particular case, there weren't any other alternatives, so we backtracked all the way up to A using our stack to keep track of where we were going. So we're back at A, and we're going to move back to Rule 1. And where can we go? Well, we're at A. Where can we go that's not already visited? Well, one possibility is we can go to C. Once again, these rules would work if we made a different decision. If we had visited D or E instead, the rules still would have worked. But we'll visit C, and we'll visit C, mark it, push it on a stack. And now we ask the question, is there any place else I haven't visited? And the answer is no. I can no longer apply Rule 1. I'm down at C, and there's no place else for me to visit. You'll notice that as I visited C, I pushed it onto the stack. So there's my stack down there. So we'll continue from here. So when we run out of Rule 1, we go to Rule 2. So we're going to pop a vertex off the stack and try to apply Rule 1. Well, the top of the stack we pop off is C. It has no unvisited vertexes adjacent. So we do another pop. We pop off A, and A still has unvisited adjacent vertexes. So we're back up at A, and we're going to apply Rule 1 again from A. So here's Rule 1 again. We're at A. So we see where we haven't visited, and we'll pick D this time. I could have picked D, but we picked D this time. So we go to D, we visit it, we mark it, we push it onto the stack, and now we're going to see if there's any place else we can visit, and there is. We can go to G. So I will visit G, I will mark it, and I will put it onto the stack, and I will look around for something else that hasn't been visited. And sure enough, there is I. So I go down and I visit I mark it as visited, I put it on the stack, and I look around, and there's no place else for me to go. I can no longer apply Rule 1. There's my stack. So I'm going to go back to Rule 2. So Rule 2, I'm going to start popping. The top of the stack is I. I pop it off, and I look at I, and I see if there's any place unvisited from I. There's not. So I do another pop. I pop G, and it doesn't have any place I can go to. So I look at the stack again. It's not empty, so I pop it. I get D, but it has no unvisited adjacent vertexes. So I pop it again, I got A. And A does have someplace else I can visit, so I'm going to apply rule 1. So I'm at A, I'll get back on the stack, and I'll go to E. Because E has not been visited, and I can no longer, I'll visit it, I'll mark it, and I'll put it on the stack, and I can no longer apply rule 1, so I go back to rule 2. I try a pop, E's on top, so I pop E, but it has no place I can go. So I try to pop again. I've got A, I can pop again. But this time I've used all the places that A is adjacent to that have not been visited. I'm out of unvisited places. So I can no longer apply rule 2. So I can't apply rule 1 and I can't apply rule 2. And so I go to rule 3 and I conclude I'm done. So the rules would say I've now visited every place in my graph. And if we look at things as we've marked them with red, it's pretty easy for us to tell visually that that is in fact the case, that there's no place left for me to go. So that's how we went through depth first search. You'll notice we got far away from A as we could until we ran into a dead end, and then we backtracked up. We backtrack up until there's another path we can take. And we keep backtracking and trying and backtracking and trying until we cover the whole graph. Or if we're looking for something particular, if I was looking for a particular vertex, I could quit in the middle of that process. So that's depth first search. So let's move on and we'll take a look at breadth first search. Breadth first search is quite similar, except we're going to use a queue instead of a stack to hold things. That means they're going to come out of the queue in a different order than they come off the stack. And that in turn means that we're going to visit them in a different order. Having said that, it's pretty similar. We're going to pick a starting point, and I'm going to pick A in a second, but I could pick any vertex and it would work. I would eventually get everywhere. So I'm going to pick a vertex and mark it, insert it in the queue, and then if there's something unvisited, I'm going to visit it, mark it, insert it in the queue. I'll keep going until I run out of places that are adjacent that I haven't visited. When that happens, I go to rule 2, and rule 2 says that if I'm out of places to go based on rule 1, I take a vertex out of the queue. A minute ago we took it off the stack, but we're going to take it out of the queue. We're going to go to that node, and we're going to try going back to rule 1 from that place and see how it works. Eventually, if we run out of places, if where we are has no unvisited places and there's nothing left on the queue, then we're done and we've covered the whole graph. So let's walk through it. Okay, so as I said, I'm going to start at A again, mostly because LaFour did. I could start somewhere else and it would still work, but I'm going to start with A. I'm going to visit it, mark it, and put it into the queue. And then I'm going to go to some place adjacent. I'll pick B. I could have picked any place. The order isn't important. As long as it's not visited, we're good. But I'll go to B in this case. And I will visit it, I will mark it, and I will insert it into the queue. And we're still at A. So now I'm going to see, is there any place else that A can go to? And the answer is yes, I could go to C. So I'm going to visit C, mark it, put it in the queue. And then is there any place else I can go to from A? Yeah, actually there is. I can go to D. So I'm going to visit it, mark it, put it into the queue. Okay, is there any place else I can get to from A? Well, yeah, actually I can go to E. So I'm going to visit it, mark it, put it in the queue. And now I'm at this point. You'll notice that I've marked with the red the different vertexes I've visited and the different paths I've taken. And I've also built a queue that's got, at this point, got A, B, C, D, and E on it. So I'm out of places I can go to from A. They're unvisited. So I'm going to start taking stuff off the stack. So I'm going to go to rule 2 and start taking stuff off the stack. So I can take A off, but there are no unvisited nodes from A. So I can take the next node off the queue. That would be B. And that does have some unvisited nodes. So I'm going to go back with my current node being B. And I don't throw away the rest of my queue, but I have taken A and B off of it. I'm going to go back to rule 1. And I'm at node B. It's my current thing, and I'm going to see where I can go to. Well, I can go to F. So I'll visit F, I'll mark it, and I'll put it on the queue. And I'll see if B has any place else I can go, but it doesn't. So I'm back to rule 2. So rule 2, I'm going to go to C. I'm going to take C, the next thing off the queue, that would be C. It has no visited nodes that it can get to. So I'm going to take something else off the queue. I'll take D off the queue. And oh, look at that. I can go somewhere. So I'll go back to rule 1. And I'm at D. And I realize I can go to G. So I will visit G, mark it as visited, and put it on the queue. So you'll see my queue now has E, F, and G on it. But from D, can I go anyplace else? No, I have no more unvisited vertices. So I'm back to taking something out of the queue. So we come back to queue, we take the next thing off the queue. The next thing off the queue would be E, but E has no unvisited nodes. So I'm going to push on and take the next thing off the queue, and that gives me F. And that does have some unvisited nodes. So I go back to rule 1. I visit my unvisited node, I mark it, and I insert it into the queue. And then I look to see whether I have anything else I can go to from F. Well, I don't. So I'm going to take, I'm going to go back to H. Yeah, I may be wrong. Yeah, start with node F. Oh, H is already there. I goofed this slide, sorry about that. H is already taken. And so there are no more unvisited vertices, so I'm back to rule 2, where I've got to take something off the queue. I take something off the queue, and I get G off the queue. So I remove G, and that has an unvisited node, so I go and I apply rule 1. So with rule 1 from G, I go and I visit I, and I mark I, and I put it on the queue. And I ask if there's any place else I can go to from G, and there's not. So I take the next thing, I go to rule 2, and I take something off the queue. So I remove H, but it doesn't have an unvisited node. I got another little bug in the slide here. I'm removing H twice, which obviously I can't do. But at this point, I've got an empty queue, and I have no unvisited nodes. So we're done. Okay, so that's our 2 ways of traversing the queue. I want to fix these slides. I don't think I'm going to re-record it. I think it's obvious enough. And boy, these things take just forever. And we'll press on with graph theory. All of this is in LaFour in chapter 13. Same examples if you want to look at it from a slightly different angle.